This is Unit 2, Video 5. In this video, we will begin learning how to name compounds. Now, the type of compound we'll be naming in this video will be ionic compounds. Remember that compounds are made of elements, and so you have two or more elements chemically combined, and that's what makes a compound. An example of two compounds would be iron 3 oxide, also known as ferric oxide. This is the form of iron oxide that's found in the red ground, red earth that's seen in many parts of the country and of the world. And there's a second type of iron oxide called iron 2 oxide, and called by an older name ferrous oxide. This is actually black iron. So we have red iron and black iron, and this is the iron that's used in tattooing. And here we will just remind you that think before you ink would be a good saying to live by. But here is an example of both of these compounds used in nature or in human affairs. So we'll learn how to name both of them. Now let's define an ionic compound. The word ionic, you can hear the word ion in there, and ionic compounds are composed of the two types of ions, cations and anions, and they are formed by a transfer of electrons. So what happens usually is there is a transfer from a metal, something like sodium, to a non-metal, something like chlorine, and sodium becomes an ion, chlorine becomes an ion, and these two ions then combine together to form the ionic compound. In this case, the ionic compound is sodium chloride, famous table salt. And what you see on the atomic scale is alternating sodium and chlorine ions. The sodium would be the blue one, this would be sodium, chloride would be the green ones, and you can actually see this order, arranged order, on the macro scale in crystal formation. Now, atoms from the S and the P blocks, remember this is the S block, this is the P block of the periodic table, will form just one type of ion. There are exceptions, of course, as you'll see, things like tin and lead, which are down below. Here's tin and lead is below tin in the P block. And you can know these from the S and the P block just by looking at the periodic table. And we taught you how to do this in a previous video. For example, we said that sulfur here will become a -2 charge because sulfur must gain 2 electrons to become like the closest noble gas, argon. And that's why sulfur has a -2 charge. The whole group of sulfur has a -2 charge. Likewise, sodium, if you take a look at sodium having 11 electrons, wants to be like the noble gas neon with 10 electrons. So sodium will lose an electron, forming a +1 charge. So these you can read directly from the periodic table. Now, if the atom comes from the D block, these are called transition elements. They'll usually form more than one type of ion. There are exceptions again. A famous exception would be silver. Silver only forms one type of ion. But these you cannot know just by looking at the periodic table, because you have two different types most of the time. An example then that we began with, there are two types of iron. This is iron 3, this is the red iron that we saw in a picture. This is iron 2, the black iron. These two types of irons exist. So just if you say iron something, maybe iron chloride, that's not enough, because you have to specify which iron you're dealing with, iron 3 or iron 2. And these we'll be able to figure out based on the compound formula, as you'll see. And we'll do some examples. Alright, now there are two types of ions. There are something called monatomic ions. The word mana means one. So these are ions formed from a single atom. The example would be chloride, Cl-, magnesium, and magnesium 2+. And these come directly from the periodic table. And then there's a very important class of ions called polyatomic ions. Poly actually means many. And so these are ions formed from two or more atoms combined. Here are two examples. This polyatomic ion has its own name. It's called ammonium. We'll see him a little later. This is called sulfate. Now it's really important to understand and to make this statement. This is a very important statement. Ionic compounds form so that the positive and the negative charges cancel each other out to form neutral compounds. So every compound that you see has to be a neutral compound, which means we'll have to match up the positives and the negatives to make sure our compound is neutral. As you'll see, this will mean, for example, if you try to match up magnesium with chlorine, you will actually need 2 chlorines because the charge is -1 for every 1 magnesium to make the 2 match up. You'll look at the charges to match them up. We'll do some examples of that. Now, we're going to show you the list of polyatomic ions. Really important list. The first, in this case 12, polyatomic ions are based on the ending 8. Now here you see chlorate, you see bromate, and you see iodate. What you'll recognize is that these are actually the halogens, or come from the halogens of group 17 from the periodic table. So here you have chlorine, you have bromine, and you have iodine, and these 3 form chlorate, bromate, iodate. You'll notice that the ending 8 is going to be very common in these polyatomic ions, 8. And there is a pattern to these. Now, in any of these, chlorate, bromate, iodate, you'll see that you have 3 oxygens. That's actually where the 8 comes from. You have 3 oxygens combined with that element. And then the charge is a -1 charge. So notice 3 oxygens with the bromine with a -1 charge, 3 oxygens with the iodine with a -1 charge. And then there is another name right above it called chlorite. The word, or the ending ite, actually is 2 oxygens. And this is related to the 3 from below. In fact, in every case where an 8 becomes an ite, 8 becoming an ite, what you see is the number of oxygens is reduced by 1. Now if you go down, if you increase the oxygen by 1, so for example if you go from 3 up to 4, you put a per in front of the polyatomic ion. Notice that per means 1 more oxygen. Same exact thing happens with the iodines. So iodate is 3 oxygens, per iodate is 4 oxygens, iodite is 2 oxygens. And then if you go 1 less than the iodite, notice the ite remains the same, but the oxygen is reduced by 1, and you put hypo. Hypo actually means not enough. In a way, think of hypothermia, not enough heat. So hypo means less. And so here you have 1. We don't write the 1, even though there is a 1 here. But you'll notice that the charge stays the same in all cases. So really all you have to do is just memorize one of these, say the chlorate, and then you can derive the rest. You can derive the perchlorate, because you know that's 1 more oxygen. You can derive the chlorite, you know that's 1 less oxygen. You can derive the hypochlorite, 1 less oxygen than that. The charge stays the same. All right, now these you have to memorize. You have to know these by heart. There is a way to see them on the periodic table, and we'll show you that. The second list of polyatomic ions now includes a bunch of the other elements. Elements like nitrogen to form something called nitrate, phosphorus to form something called phosphate, sulfur for sulfate, and then we have carbon forming carbonate. Now, some of these patterns, now let me show you another pattern. Here's carbonate. Carbonate has 3 oxygens with a -2 charge. And then if you put a hydrogen in front of it, it becomes hydrogen carbonate. The older name for this is bicarbonate. Bi just means you've added 1 more hydrogen to have a binary ion. So what you have here is a hydrogen from the periodic table. If you take a look at hydrogen, hydrogen forms a +1 charge. So when you add a hydrogen, the -2 gets reduced down to a -1 because the hydrogen ion reduced it, and that's kind of the idea. You can see the same thing happening with phosphate. So phosphate has a -3 charge, and then if you put a hydrogen phosphate in front of it, it becomes a -2 charge. If you put dihydrogen phosphate, 2 hydrogens, it becomes a -1 charge. So you can see that pattern here as well. You also see the previous pattern that we saw on the screen above, where if you have an 8 turning into an ite, you lose an oxygen. Here is an oxygen lost. Now, the difference that you will note from the previous is that the charges for the 8 was -1 for chlorate, for example, if you go up above. But here the charge is different. The charge here for the 8 is -3. And for the nitrate, it's still -1. But for the sulfate, it's -2. So there has to be a way of memorizing this. Now, there's an interesting saying that you can use to memorize this slide. And the saying goes like this. Nick the camel, it's about a camel actually, Nick the camel ate, which means has eaten, ate clam supper in Phoenix. So this is a story about a camel who enjoys some clams. Now, what this shows you is this shows you the 5 polyatomic ions. This one here, Nick, camel, clam, supper, and Phoenix. Now these are the 5 polyatomic ions. Nick represents nitrogen, or nitrate. Camel actually represents chlorate, which was on the previous screen, and chlorate, clam represents chlorine, apologies. Camel represents carbonate, there it is, because Ca is carbonate, Cl is chlorate, which is on the previous screen. If you know chlorate, you know all the rest of them on the previous screen. Supper represents sulfur, sulfate, and phosphorus for Phoenix. Now, the way this helps you memorize these polyatomic ions is you take a look at the word Nick, and you count how many consonants it has. Now the consonants, in this case, are 1, 2, 3 consonants. So nitrogen gets 3 oxygens. If you take a look at the camel, this is representing carbon. Alright, let's ask how many consonants we have. We have 1, 2, 3 consonants. You also have 3 oxygens. Now if you take a look at supper for sulfur, in this case you have 4 consonants. 1, 2, 3, 4 consonants. So 4 oxygens. In the case of Phoenix, you have 1, 2, 3, 4 consonants. Again, for phosphorus, you have 4 oxygens. Back to clam. Clam is chlorate, so chlorine has 3 oxygens. So notice the amount of consonants tells you how many oxygens. The second part of it would be the vowels. The vowel, in this case, the number of vowels tell you the charge. So in Nick, we have 1 vowel, that's a -1 charge. In camel, we have 2 vowels, that's a -2 charge. In clam, we have 1 vowel, -1 charge. Just 1 vowel. In Phoenix, notice 1, 2, 3 vowels, that gives you a -3 charge. And again, in sulfur, you get 2 vowels, here they are, with a -2 charge. So this allows you to memorize the 5 most important polyatomic ions, and then you can derive the rest. In other words, if you know what phosphate is, you can go down to phosphite by having the rule that ite is 1 less oxygen. Alright, so hopefully this makes sense. You actually have to memorize all these as well, so put memorize. And then we'll work with them in class. Memorize these. And then finally, we have one more list of polyatomic ions. Now these are also very common, and I'll leave it up to you to find a way to memorize these. We also have to memorize these polyatomic ions. And memorization is a good exercise to be engaged in. It develops the brain and your confidence. Some of these really important ones, let me just circle extremely important ones which you'll see again and again. Ammonium is very unique. Ammonium is actually the only polyatomic ion that has a positive charge. So here's ammonium. Notice that's a positive charge. Everything else is negative. Ammonium has a positive charge. Hydroxide is extremely important. There's one set of compounds called bases that are based on the hydroxide polyatomic ion. You can hear hydrogen and oxygen, hydroxide. Permanganate is my favorite polyatomic ion, so you'll definitely have to memorize it. Here's permanganate with -1 charge. Acetate is actually found in vinegar and found in foods, food-like compounds, so very important to memorize that. Chromate is very beautiful in its colors, so definitely memorize chromate and its cousin dichromate. And then cyanide, here's cyanide. Cyanide is very important. Cyanide is a poison, and Cn with a -1 charge. Cyanide also has the same initials as Chuck Norris, and that is not a coincidence. So make sure you memorize that as well. And then some of these other fun ones down here, thiosulfate, and then thiocyanate. We'll use a few of these in our labs. All right, so we'll finish the video here, and then we'll do some example problems in the next video.